Are there specific processes where B minus L is violated? Yeah, I mean, I'm not sure exactly what you mean by specific process. In the high temperature, right, you can have processes where a proton becomes a positron, for example, right, plus other things. Right? So the total baryon number can be violated. I mean, actual process is more complicated because it turns out the baryon number is violated, but you need violation of lepton number in all generations, right? Because like Le minus L mu is conserved, right? So just a proton going to electron will have this problem that Le minus L mu is not conserved, right? Because proton has no Le minus L mu, right? The final state will have Le minus L mu equal to 1 or minus 1 because it's positron. So, but you can, I mean, so consistent with this conservation laws, right? We know that B minus L is conserved and all this Li minus Lj is conserved, right? Difference between lepton numbers. Any process that you can write down which satisfies these conservation laws can happen, right? And will happen. Yeah, so you have to produce a positron plus 2 antineutrinos, for example, right? Where all the Le minus L mu is a conserved, exactly. Right? So you have to combine things appropriately, and then you can show that then this process can take place. Yes, electric charge, of course, is conserved, right? So, and low energy, the hypercharge, you don't have to worry because that is spontaneously broken. But we wrote down 5 charges, right, which are relevant for high energy processes, right? These 3, B minus L, Li minus Lj, there are 2 of them, and the electric charge and hypercharge, right, of which the 4 are conservation laws that must hold also in low energy. Any other question? Okay, so let me then start by writing down some of the formulae that we arrived at yesterday. So we introduced these 2 matrices MKL, which is sum over alpha, G bar alpha, and okay, let me first define this. So this one, so all this sum over alpha runs over all particles. This gives the nth conserved charge carried by alpha-th particle. Its antiparticle carries opposite charge, so that we don't have to write separately. And this G bar alpha we define as 2 G alpha for bosons, G alpha for fermions. Okay, this is just the degeneracy of states. These are for relativistic. Where you can, we set the mass to 0. Okay. But in general, there may be a more complicated formula, right? Whatever you get from the integral is what we will define as the G bar alpha. And then we wrote down a formula for V. Okay, let me write the formula for B. Okay. The baryon number NB was written as sum over LK VL M inverse BK M inverse KL and N tilde K, where Vk was sum over alpha NL. Thank you. This is L. So here, these of course we have already defined, and B alpha is the baryon number. Baryon number of alpha particle. And in this formula, then n tilde n is the density of Lth conserved charge. So the idea is that if we know these n tilde L's, right, how much conserved charge of Lth type there is, okay, and that in principle is determined by some high energy process, right, whatever produce these conserved charges, because these are not strictly conserved. Okay. Once you know this, then you can use this formula to calculate the baryon density. Okay, and this formula is valid as long as the system is in equilibrium. Right? Once you have an equilibrium system, you can calculate this without knowing anything about the history. The only knowledge about the history of the universe is contained in these n tilde L's. Okay, how much conserved charge of each type was produced. Is this okay? So today we are going to analyze this formula in a little more detail for the specific case of the standard model, right, where we want to look at the baryon production. So in the standard model, the conserved charges are B minus L, Y, Le minus L mu, Le minus L tau, and I3. So, and Q, let me write the formula for Q. Q is, Y is basically I3 minus Q. So Y is I3 minus Q. Okay, from the perspective of the Lagrangian, this is the U1 charge that you have in the that you write down introducing the standard model, and I3 is the third component of the SU2 generator. Right? That's the definition of these generators, and Q is a particular combination of Y and I3. So the first we will try to establish a relation that I mentioned last time, okay, that the matrix M is block diagonal so the 2 by 2 block involves B minus L and Y, and then the other block involves Le minus L mu, Le minus L tau, and I3. Okay, and similarly here, Le minus L mu, Le minus L tau, and I3. Okay, so let's try to prove this first, okay, because this will be useful. So what we need to do to prove this is to show that if one of the index, when you look at MKL, that if this index is either B minus L or Y, and this index is I3 Le minus L mu, Le minus L tau, then this is 0. Right? That's what I mean by block diagonal. Right? There is component of the matrix between first two and last three will be 0. Is this clear? Right? This is what we are trying to prove. So let's pick L equal to I3. The formula for M is sum over alpha G bar alpha CK alpha CL alpha. Now I claim M is symmetric, right? By construction, so it doesn't matter. I mean, once you have proved one way, that's enough. So the result that I claim is the following: that for every alpha, either CL alpha is 0, okay, in which case it doesn't contribute. L is I3 in this case. Either CL alpha equal to 0, okay, or there is an alpha prime such that CK alpha equal to CK alpha prime and CL alpha is minus CL alpha prime. Suppose this is true. Okay, we'll argue in a minute why this is true. Suppose this is true, right? Then it says that if the first case holds, the CL alpha is 0, then of course it doesn't contribute to this. If the second case holds, that CL alpha is not 0 but this property holds, then you can clearly see that the contribution from alpha, and I should also say G alpha equal to G bar alpha equal to G bar alpha prime. Then the contribution from alpha and alpha prime cancel, right? Because they will differ by sign. G bar alpha and G bar alpha prime are the same. CK alpha and CK alpha prime are the same, but CL alpha and CL alpha prime have opposite sign. So when you add sum over alpha, they will just cancel. This is for? Only for L equal to I3. This will also be true for the other cases. Right? Right now we are trying to do it for L equal to I3. Is this statement clear? Now let's see why this is the case. And the argument in fact is very simple. That I3 is part of an SU2 group. Right? And SU2 comes with its representations, right? So a trivial representation of SU2 is the singlet, right? Which means it doesn't carry any I3, right? Just like the spin 0 particle in for SU2. If it's not a singlet, then I3 is always come in equal and opposite pair. Right? Doublet, for example, has I3 equal to half and I3 equal to minus half. Right? A triplet will have I3 equal to 1, 0 and minus 1. Okay? So there are always in a multiplet elements which have opposite I3. And the point is that those elements with opposite I3 will always have the same value of these global charges. B minus L is a global symmetry. Okay? Global symmetry always commutes with gauge symmetry, SU2. And it will also have the same value of Y because Y is part of a U1, right, which also commutes with the SU2 group. So if SU2 is converting an I3 equal to half to I3 equal to minus half, then it doesn't affect the B minus L value or the Y value. So that's the argument that given any alpha, there is always an alpha prime which has this property. That it doesn't change the B minus L value, but it changes the I3. And G bar is the same because it's the same part, same multiplicity, right? Because the SU2 transformation doesn't change the multiplicity. Right? If it has a spin 1, it will remain a spin 1. If it has a spin half, it will remain a spin half. Is this point clear? Okay. So example of such pairing are U and D, for example, right? U and D. Okay, so U have I3 equal to half, D has I3 equal to minus half, but they will have the same B minus L and same Y. B minus L is clear, right? Both of them have B minus L equal to 1/3. Right? They'll also have the same Y, right? I'll later on list the values of Y and B minus L and everything else for all the particles of the standard model. Right? But this is the argument. Is this clear?
So this argument relies on the fact that we can represent the SU2 in some spin J representation.
Exactly. Right? That any SU2 representation either has I3 equal to 0, right? That it's a singlet, or it always appears in positive and negative pairs. Okay. Now a similar argument holds for LE minus L mu, right? So if we take L equal to LE minus L mu. Okay. The same claim is true. Okay. Namely that either Cl alpha is 0, okay, or that there is always an alpha prime for which this happens. So now let's say given an alpha, how we choose our alpha prime. Okay. So if alpha happens to be not a lepton, right, then of course Le and L mu are 0, right? So Cl alpha is clearly 0. If it is a lepton, then you simply exchange its mu and E identity. If it has a mu, you make it E. If it's E, you make it mu. Right? If it's nu mu, you make it nu E. If it's nu E, you make it nu mu. Right? Just exchange the electron and muon identities. For tau, again, Le minus L mu is 0, so you don't have to worry. Right? If it's either the electron lepton or a muon lepton, right, then you simply change its identity to the same particle. That changes Le minus L mu, the sign of Le minus L mu, right? Because Le minus L mu will become negative of itself, right? When you make an E into a mu or a mu into an E. But electrons and muons otherwise carry the identical quantum numbers, right? These are just generations, right? Different generations have identical representation under SU2. So neither B minus L nor Y is going to be affected by this flip between E to mu and mu to E, right? Because L is the sum of all three lepton numbers, right? Le plus L mu plus L tau. Okay. So L doesn't change, B doesn't change because B of course is 0 for the leptons. Okay. So then this is so the same argument that we gave here is also true for Le minus L mu. Because muon and electron, the two multiplets, right, transform identically under the SU2 times U1, right? So if whatever Y electron has, the same Y will be shared by the muon. Whatever Y neutrino has, the same Y will be shared by the neutrino. Right? Here you also have to distinguish between left and right. Right? Left-handed muon and right-handed muons have different Y. But it doesn't matter, you exchange left-handed muon with left-handed electron and right-handed muon with right-handed electron. Right? Those have the same Y. Only the Le minus L mu will change sign.
I3, what happens
I3 will also remain unchanged, indeed. So I3 will also remain unchanged. Right? But that's in the other block, right? So you don't have to worry about this. Right? But it is true that I3 will also remain unchanged. So that this last three block will have a further block diagonal structure, right? 1 and 2. Okay, but we don't worry about this because it's the first 2 by 2 block that will be important for us. Is it clear? And the same argument for Le, same argument for Le minus L tau. Next, we will make another claim. That Vk is non-zero only for k equal to b minus L or y. Okay. So Vk, let me remind you the formula. Vk was sum over alpha, g bar alpha, ck alpha, b alpha. Sorry, this is, if it's k here, it's better to be k here, right? And here we prove it more or less in the identical way, that if k is equal to I3 L e minus L mu or L e minus L tau, then for every alpha, either ck alpha is equal to 0 or there is an alpha prime such that b alpha equal to b alpha prime and ck alpha equal to minus ck alpha prime. And the argument is identical. Okay, if say k happens to be I3, then we just exchange the appropriate elements of the SU2 representation. Right, I3 equal to half, you exchange with I3 equal to minus half, and that doesn't change the baryon number. Okay, baryon number is not affected by changing U to D, for example. Right, they have the same baryon. Similarly, Le minus L mu, right? You just exchange the electron and muon identity. Right? Electron and muon both have baryon number 0. Right? So it again doesn't change the baryon number. Okay. So using that, you can prove that Vk has only the first and second component 0, non-zero, right? The B minus L component and the Y component. Is this point clear? Okay. So now we are going to do some explicit calculation of this matrix M and the vector V. Right? Because once we have that, then we can just substitute in this to calculate NV. Okay. And in fact, as we discussed last time, in N tilde L, the only non-zero value in this 2 by 2 in that two-dimensional space, right, the only non-zero N tilde L comes from N tilde B minus L. Right? Because N tilde Y has to be 0 because it's a gauge charge. Right? And the gauge charge you cannot produce from nowhere. Okay, so on this side there is N tilde B minus L. So you already know that this vector, N tilde L vector, is basically proportional to 1 0. Right? Only B minus L is non-zero. Right? For Y it is 0. So this vector you already know up to this constant of proportionality. So if you can calculate V and M, we have got the result for all the baryon number.
B minus L will not change because it is a global charge.
Yes, B minus L is a global charge. Yes.
And why with option? Because one charge and
Yeah, that when you make an SU2 transformation, right, SU2 commutes with B minus L transformation, right? So different, so you are going from one element to another, right, upper component to lower component using an SU2 transformation. That doesn't change the B minus L charge, right? Because once you say SU2, it commutes with all the other groups, right? The only non-commutativity is within the SU2 itself. Okay, so I'll write down the spectrum. I think it will also become visible from that perspective. So the standard model spectrum. Okay, I'll write down the relevant part of the standard model spectrum. For example, the W and Z bosons play really no role. Okay, so I'll not write them here. So we need the particle type, then B, L, Y, and G bar. Okay. So we start with, and we have to separately list the left and right-handed components, right? Because as I said, the left and right-handed components I3 and Y take different values for left and right-handed components. Okay, I3 we are not interested in now because we are only looking at the 2 by 2 block, right? But Y can take different values for the left and right-handed components. So that's why I have to write separately UN and UR. So UL, D is 1/3, left hand number is 0. Okay. Y, one way to identify Y is that this is I3 minus Q. In fact, originally it came because Q came from Y minus I3. Okay. Sometimes one also writes this as Y by 2. Okay, that depends on a normalization. I have just chosen the normalization so that I3 minus Q is Y. So Y is minus 1/6. And G bar is 3. This 3 comes from the SU3 quantum numbers. Because it's a 3-dimensional representation of SU3. Right? So SU3 is not going to play any role except that while counting how many degrees of freedom you have, right? Because that enters the formula, right? The partition function. We need to know how many states there are, right? So the 3 of them. Okay. And we have not counted this factor of 2 because of for the spin, right? Because left and right helicity states will be counted separately, right? Because their charges are different. Okay, so that's why there's no further factor of 2 here. So this minus 1/6 basically is a result, if you can calculate from this formula, half minus 2/3. Right? The I3, U is the upper component, right? So I3 is half, and the charge that U carries is 2/3. Okay, that's where this minus 1/6 comes from. So DL, okay, again, let me emphasize that when you write down the standard model Lagrangian, right, you put this in first, right, and then Q comes out to be minus 2/3, right, that's an output, but here we are just using that insight to figure out what Y value should be. Okay, DL 1/3, 0, minus 1/6, 3. Okay, this, yeah. So for DL, okay, you see I3 is minus half, okay, and Q is minus 1/3. Right? So this minus 1/6 is coming from minus half plus 1/3. Okay. But by our previous argument, they must carry the same Y, right? And you do see that indeed they carry the same Y, right? Because U1 commutes with SU2, so they better carry the same Y. So if this calculation leads to somewhere where the 2 elements of the doublet do not carry the same Y, then you know that there is something wrong in this calculation. Okay, so UR again 1/3 0 minus 2/3 3 dr 1/3 0 1/3 3 new L 0 1 half 1. Okay, there's a color here, so here the degeneracy factor is 1. Then L is 0 1 half 1. ER is your y is oh, something is wrong. No, this is fine. Minus 2/3. Yeah, these are I3 equal to 0. Okay, because these are right-handed particles are SU2 singlets. Okay, left-handed ones are SU2 doublets, right-handed ones are SU2 singlets. Right, so I3 equal to 0. So that's why it's 0 minus 2/3. Right, and this is 0 minus 1/3. So for these y is not the same because they are not related by SU2. Right, only the left-handed ones are related by SU2. Similarly here, nu L and EL are related by SU2. Okay, that's why the y values are the same. For ER, its y value is 1. And then we have the two scalars, phi plus and phi 0. This is 0, 0. They don't carry any value or a left hand number. These are the Higgs fields. Okay. Then minus half and 2 and minus half and 2. Okay, and in fact you also have to include its complex conjugates, conjugate fields. No, sorry, you don't include the complex conjugate fields because that's already counted in the analysis that we did, right? We are only counting the particles. The antiparticles are already counted as minus n bar alpha, minus n alpha bar, right? So you don't list them separately. That's why in this list I have not included any of the antiparticles. Okay, only the particles. These two basically comes because they are bosons. Okay, and if you recall for the bosons there is a factor of 2. So now let's just do one calculation from here. The rest I'll leave as an exercise. So let's calculate the B minus L component of this. So from this formula, well, that formula I have erased here. Okay. Basically, you have to multiply the B minus L charges, right? Both are B minus L in this case, multiply by that G bar factor, and then sum over all particles. Right? So you have to basically go down this column and sum over everything. Okay. So the first will be 1/3 times 1/3 times 3. Okay, I'll write all the sums explicitly, right? Even though many of them are equal. That's coming from here, right? B minus L is 1/3 times 1/3 times 3 coming from G bar. Then we again have 1/3 times 1/3 times 3 for the second one, right? Third one, fourth one, all the same. 1/3 times 1/3 times 3. Nu L has B minus L equal to minus 1, right? Because B is 0, L is 1. Okay. So plus minus 1 times minus 1 times 1. EL is the same, ER is the same. And these don't contribute because they have 0 B minus L. Right? So when you add them up, this is 12 plus 3. Okay, I have got here, sorry, not 12. They are 1/3 each, right? So 4/3 plus 3, that is 13/3. This is for one generation. So the actual formula M B minus L B minus L is 13/3 times Ng, where this is the number of generations. Is this clear? Similarly, you can calculate the B minus L Y, right? All that will happen is that these two factors will remain the same. The second one, right, instead of having the B minus L values, you have to use the Y values, right? So minus 1/6, the first will be multiplied by minus 1/6, then minus 1/6, then minus 2/3, 1/3, and so on. Right? That will be B minus L Y, and similarly Y B minus L will be the same, and then Y Y you have to multiply this with itself. Is this clear? So I'll leave it as an exercise to check. That M has the structure 13/3 Ng. This you already saw here. Minus 8/3 Ng. And here is 10/3 Ng plus Nd. So Nd here is the number of Higgs doublets. Okay, normally we use only one Higgs doublet, right? This phi plus and phi 0. But in principle, in the standard model, you can include multiple Higgs doublets, right? And write a more general potential. It will be a little more complicated, but the physics is more or less the same. Okay, so if you want to introduce multiple Higgs doublets, right, you just have to multiply by Nd. Okay, but in the what we usually call standard model, right, Ng is 3 and Nd equal to 1. Right, that's what we'll be using. So for Ng equal to 3 and Nd equal to 1, we get M as 13 minus 8 minus 8, and this is 10 plus 1, 11. And M inverse is 1/79. Okay, I wrote M inverse because M inverse is what enters this formula. I'll also leave it as an exercise to check. You remember the formula for Vk? Okay, the calculation is identical, okay, except that in the when you take these products like this, the second element, okay, is as it is. It's either b minus l or y. Right? That's what we'll pick. For this, you'll pick the baryon number. Okay, which for these three it is 1/3, okay, but for the others it is 0. Is it clear? Right. So once you have gotten the table, then you can calculate everything. Okay. And finally, I have not written down the W plus W minus, right, which are also particles in the standard model, okay, because W plus and W minus do not carry either B or L or Y. Right. So in the B minus Ly sector, right, they have no contribution, because we don't have to worry about W plus W minus or the gluons, right, carriers of the strong interaction. So this is the result is 4/3 Ng and minus 2/3 Ng. So, and I should say others are 0. This we had already argued, right? That these will be all zeros. So this for us will be 4 minus 2 and 0, 0, 0. Okay, so I think I can erase this now, and we will be using those formulae. So if we want to calculate NB now, we have this structure. This is 4 minus 2. 4 minus 2. These are all zeros. Then M or M inverse. So let me write this 1/79 here. 1/79. M inverse has that structure 11, 8, 11, 8, 8, 13, 8, 13, and then these are all zeros because of this block diagonal nature. And here, as you will see, we don't really care what it is. And then you have here n tilde b minus l 0, and here again we don't know what it is. Okay. So let's first multiply these out. Okay, because here it's simple. So this is 1/79. times you get 44 minus 16, that's how much, 28. Then 32 minus 26, that's 6. Then these are all zeros. Is it clear? So these things didn't matter, right? Whatever these are, because these are all zeros. Right? So the last three elements are all zeros because these multiply 0 and these multiply some non-zero result, but you always have a factor which is 0. Okay, so you have this structure 28, 6, 0, 0, 0, and then you have n tilde b minus l 0 and then something else. Okay. So this gives you 28 over 79 n tilde b minus l. Okay, this is the result I described yesterday. Right, and then you showed that based on this result, you can also estimate the number of leptons, right? And then since you already know the electron density, which is equal to the proton density, right, you can figure out how many neutrinos there are, right? How many excess neutrinos there are. Right? So this was the key result from this. Now you may want to know more. Right? Instead of saying how many excess neutrinos there are, right, you may want to know how many excess electron neutrinos there are and how many excess muon neutrinos there are, how many excess tau neutrinos there are, right, individually. Okay, this analysis doesn't tell you that. Right? For that, you have to also include the other block, right, the rest 3 by 3 block, because that, if we are now interested in those, right, those charges are here, right, Le minus L mu and Le minus L tau are in the last 3 block, right, and if you are trying to get information on those, then we need to know these, right, the original n tilde, right, what kind of excess it produces. I mean, we said there is B minus L, right, but what about Le minus L mu or Le minus L tau, right? We have not said that, said how much that is, right, because that is not relevant for calculating the baryon density. But if you want to calculate the difference between lepton densities, you need that. Okay. So in fact, one of your assignment problems I think involves this, right? It asks for calculating individually the electron muon and tau lepton excess.
Until the y will still be 0.
Pardon?
Until the y will be.
Y will be 0 because y is a gauge charge. Exactly. Okay. So because these are gauge charges, right, you don't expect them to be produced in the early universe, right, because they are exact symmetries. Now all this assumes, of course, that in the early universe there is some B minus L violating interaction, right, which is clearly beyond the standard model. As I said, in the standard model, B minus L is a non-anomalous symmetry, so it is not violated, right. So you have to go beyond the standard model. Is this point clear? Okay, so in the rest of the lecture today, I will try to describe, okay, what kind of new physics could possibly produce non-zero B minus L or B or something else. Okay, that's what kind of new physics we need. So, possible new physics beyond standard model. So the one popular class of models are what are called grand unified theories. So originally these are designed to unify these three groups that we have, right? The standard model has SU3, SU2 and U1, right? The grand unified theories were designed to unify all of them into a single group. So the minimal one of this, right? The minimal choice is SU5. So SU5 is a 5 by 5 unitary matrix, right? So basically the SU3 sits in the first 3 by 3 block, SU2 sits in the last 2 by 2 block, okay? And the U1 basically is the diagonal 1 1 1 and diagonal minus 3 half minus 3 half, right? But the trace has to be 0 because it's in the as a generator, it's a, U1 is a diagonal 1 1 1 and minus 3 half minus 3 half. That's the way the theory was designed. Okay, and you can show that it is possible to write down a theory which has SU5 as the gauge group, and the standard model can be unified, right? Instead of having so many different representations for U and D and UL, DL, DR and so on, right? In this grand unified theory you only have two representations, right? You can fit all the particles into just two representations. Every generation can be represented as a two independent irreducible representations. But the important point for us is that this one has baryon number violation. So this has extra gauge bosons clearly, right? So first of all, it has extra gauge bosons. So how many gauge bosons are there in SU5 altogether? The number of generators of SU5. Number? Pardon? 24, right? N square minus 1 is the formula, right? So it has 24 generators, of which some are of course standard model generators, right? So 8 are strong SU3 plus 3 comes from SU2 and then 1 is the U1. So you are left with 12. This leaves 12 extra bosons. And in terms of the generators, if we represent as 5 by 5 matrices, right, these 12 extra bosons are basically the 6 on the upper right hand block, right? It's 3 times 2 block, right? 6 from the upper right hand and 6 from the lower right hand. Okay, that's lower left hand, right? That's the way you think of these extra gauge particles. Okay. Now, of course, we don't see SU5 at low energy, so SU5 has to be broken. Okay. And this breaking happens at a high scale, right? So the model is designed in such a way that SU5 is spontaneously broken, just like the standard model SU2 is spontaneously broken by the vacuum expression of the Higgs field. Similarly, SU5 is also spontaneously broken at a very, very high scale. Okay. And that then below that scale, it's as if we have just SU3 times SU2 times U1. Okay. Just like in the standard model, right? Below the electroweak symmetry breaking scale, okay, the gauge group looks like SU3 times U1, right? The W and Z bosons become heavy. Yeah, so similarly, here there are extra gauge particles which are called X and Y bosons. These are X and Y bosons, and these become heavy. Now, in our context, these are important because these gauge bosons can lead to proton decay. Okay, so for example, we have diagrams like this. Okay, so time flows up. You can have U two U's under X boson exchange becomes U bar and E plus. Does that sound right? This doesn't sound right. This is D bar. Okay, let me just. The charge has to be conserved, right? That's the way you have to figure out what this could be. Any guess of what that extra particle could be? Pardon? Let me see the diagram. Sorry, this is U and D. U and D going to U bar and E plus. Because this has total charge 2/3 minus 1/3. That's 1/3, right? 2/3 minus 1/3, and this is minus 2/3 plus 1. That's also 1/3. Right? So total charge is conserved. So there are processes like this. Now, why is it useful? Or useful for our purpose? Because you see, if we have UUD, this is a proton, right? Proton is a UUD. And then this UUD under an X boson exchange can become E plus and U bar U. So this gives you it for proton to decay into E plus pi naught. U bar forms pi naught. Right? So this is a channel for proton decay. Right? So if there are X bosons like this will induce proton decay. Okay, so and that of course causes baryon number violation. Pardon? Yeah, it does violate Le minus L mu also. Yes, this yes. So I mean those are all global symmetries, right? So at high energy they can't be violated. So it does violate Le minus L mu. Okay. And in fact, this process is used to put a limit on how massive the X boson could be, because we know that proton is very stable, right? Proton lifetime. So the P lifetime is of order 10 to the power minus 34, well, less than or equal to 10 to the minus 34 years. Sorry, 10 to the plus 34 years. Okay, which means proton is very, very stable, and that puts a limit on the X boson mass. So mx, so this implies that mx has to be larger than 10 to the 16 GeV. Okay, so the symmetry breaking has to happen at a very high scale. But these kinds of models, granular unified theories, right, are useful for baryogenesis, because in principle they can lead to baryon number violation. Pardon? Oh, people have looked for proton decay, right, in big detectors. Right, if proton decayed, you would have seen some stray E plus coming out, right, and that will be detected in the detector. So by looking at that, I mean, of course, you cannot wait for 10 to the 34 years, right? But we have a lot of protons, right? So we don't need to wait for 10 to the 34 years to see this lifetime. As long as you have a lot of protons, you can see what fraction are decaying. Okay, now this is good, but only problem with this is that this process doesn't violate B minus L. Right? You can see proton goes to E plus. Something is wrong. Yeah, maybe L. Oh, B minus L. Yeah, you're right. Okay, so B minus L is one on this side and one on that side. Right? And in fact, you can show that all the other processes, including Y boson exchange, in SU5, right? Whereas Le minus L mu is not conserved, right? Le minus L tau is not conserved, but B minus L is conserved. Okay, this is specific feature for this SU5 granular unified theories. But once you know that this B can be violated, right? If there are other granular unified theories you can construct which also violate mu minus L. Yeah, so but this is general principle that you introduce extra gauge bosons, right, and their exchange can violate some of the conserved charges that you see in low energy. Are there questions on this? So what I'll discuss now is a minimal modification of the standard model that can possibly violate mu minus L. And like the grand unified theories, this modification also has the feature that it serves other purposes. Right? Just like grand unified theories were originally designed to unify the gauge group, right? This modification that will be described was also originally designed to explain some things which I'll describe, right? What it was designed to explain. Okay, but again, you have to go beyond the standard model. So the point is that we already know, that standard model has massless neutrino. And this contradicts experiment. Right? Because you know the neutrinos are massive in experiment. And in order to give mass to the neutrinos, we need to introduce right-handed neutrinos. Right? So this requires, so we need right-handed neutrinos. Okay. So the minimal version of this is to introduce 3 right-handed neutrinos okay, which I'll denote by nu IR with I equal to 1, 2, 3. Okay, 3 because if you want to give mass to all 3 neutrinos, right? We don't actually know if all 3 neutrinos are massive, right? If not, maybe you can get away with 2 right-handed neutrinos. Okay, but let's assume that you want to give mass to all 3 neutrinos, so you need 3 right-handed neutrinos, and these are taken to be singlets neutral under SU3, SU2 times U1. Of course, it's neutral under SU3, right? So it's neutral under the full gauge group, right? Just it doesn't transform at all under any gauge symmetry, at least not the standard model gauge symmetry. So the point is that if they are taken to be neutral, we cannot directly combine neutral and the left-handed neutrinos to right-handed neutrinos, right? Because the left-handed neutrinos are part of a doublet. Right? They transform as the spin-half representation of SU2. You cannot just combine, have a quadratic term, one of which is in a spin-half representation, and the other one is in the spin-zero representation of SU2. Right? So that's not possible. But the way one gives mass to this is that one introduces a gauge invariant coupling of the following form. You can take this to be diagonal if you want, but that's the simplest case. Plus Hermitian conjugate. Okay, so in other words, you just think of this as two component while spinners, each of these. Okay, that Dirac index I am not writing here, right? It's understood. So when I am writing nu bar, right, it's basically nu dagger gamma naught. That's the way you will think of this. Right? Then it's multiplied by phi 0 star and phi plus star, and then multiplied with nu rj. Right? So if I want to write it out explicitly, it will be sum over ij equal to 1 to 3 lambda I. These are just some constants. Nu bar li nu rj phi 0 star plus nu e bar li nu rj phi plus star. Okay, so these look like not mass term but the interaction terms. But then once phi 0 star gets vacuum expansion value, we get effective mass of the neutrino. Right, because then once you see, this doesn't get vacuum expansion value, right, because this is charge field. The Higgs field, the neutral component, gets vacuum expansion value, so this gets vacuum expansion value, and then that gives a quadratic term involving nu L and nu R, and that's exactly what we call the mass term, right. So this is the mechanism by which one can give a mass to the standard model neutrinos by adding extra singlets, right. Normally you don't include the singlets in the standard model, but you can easily do it, right. It's not doesn't require doesn't require, for example, reformulation of quantum field theory or anything, right. Just a minimal modification by adding some singlets, you can give mass to the neutrinos.
We see that this doublet coupling term is case invariant.
Because that's why I have written it this way, right. That this is a doublet, this is a doublet, right. So when you multiply, it's SU2 singlet, right. For the y, you have to check, right. These have some y charge, and you can show that this has exactly opposite y charge, because this doesn't have any charge at all, right. So you have to just check that this y charges just cancel out, right. That's why you have to put this conjugate, right. Otherwise, you could have made phi plus phi 0. That's also a doublet, but that has the wrong y charge. Yes, in order that y charges of the charge of this and these are opposite, we have to do this, take this conjugation. Okay, now let's look at the symmetries, right? Does it violate B minus L? Right, of course, nothing carries any B, right? So the real question is, does it violate L? Right? If it violates L, it will also violate B, right? Because the neutrinos are B neutral. Okay? And so for this, okay, so we already know that nu L I goes to e to the I theta times nu Li. ELI goes to e to the I theta times ELI. So this is a lepton number, lepton charge. Right? So lepton charge comes from symmetries of this kind. Right? And since I'm talking about a total lepton number, I have not used different phases. I have used the same phase for all leptons. Right? If you want to have different phases, you have to introduce theta I there. And now we want to check whether this is a symmetry. Now to check whether this is a symmetry, we have to know how nu R transforms. Right? Nu R is a new field that you have introduced. Right? And when we say that you want to check if this is a symmetry, right, what you should really check is it possible to assign some symmetry transformation to nu R so that the Lagrangian is invariant. Right? You can always arbitrarily choose symmetry transformation of nu R that doesn't leave the Lagrangian invariant. Right? But what we are looking for is whether there is a symmetry assignment that you can make to the nu R that makes the Lagrangian, keeps the Lagrangian invariant. And in this case, it's clear that it is indeed possible to make such an assignment. You just take nu Rj going to e to the I theta nu rj. Because the nu bar r will give, so nu bar L has e to the minus I theta, right? That will combine it to the I theta and cancel, right? So it is this Lagrangian, and if you make this assignment, the Lagrangian is invariant under lepton number transformation. So L is conserved, there should be minus L violation.
Our assumptions that this is neutral under SU2 E1.
No, because that's a global symmetry, right? So we have to make sure that the global symmetry commutes with the SU2 and U1 transformations, right? Here there is only a singlet, right? So you have to make sure that all multiplets in all fields in a multiplet transform in the same way under a global symmetry, right? Here there is only one field in the multiplet, right? The nu r. So you can assign anything that you like. Is this clear? Okay. Now you can ask that given this, okay, we have already introduced some fields. Okay, what other gauge invariant terms you can add to the Lagrangian? Is it clear? Right? What other gauge invariant terms you can add to the Lagrangian? And it turns out that it is possible to add another class of gauge invariant terms to the Lagrangian that only involves the news. So we can add
Can you just remind me what was the I index there?
I is the I runs from 1 to 3 generation index.
Generation.
Right? You have introduced 3 neutrinos, and the point is I could have taken the lambdas to be diagonal, right, which is the simplest case. The electron, right-handed electron couples to right-handed neutrino and so on, but in general you can introduce a matrix. Okay. So we can add new kinds of coupling, new kind of terms to the Lagrangian, and that's the following. Where nu or C, this is the charge conjugate of nu r. Now I will not try to explain what charge conjugation is, but if you recall your lesson from QFT1, right, given any Dirac field, right, or even Weil field, you can define a charge conjugate field, right, which involves complex conjugation and whose Lorentz transformation laws are identical. Okay, the Lorentz transformation laws are identical, but the parity gets reversed. Okay, so this effectively behaves like a left-handed particle, left-handed spinor. And because it behaves like a left-handed spinor, this nu bar nu c bar nu, okay, is a Lorentz invariant term that you can write down. So if we add this term in the Lagrangian, okay, let me say why this was introduced in the first place, right? Because this term was introduced even before you talked about this baryon asymmetry, etc. Okay. Then if we add this term to the Lagrangian, right, then the mass matrix, see, there are different kinds of mass terms now, right? This, once you give the phi 0 vacuum expectation value, you get this cross term between nu L and nu R. Okay. So those cross terms, so the mass matrix takes the form that these are lambda times V roughly. So where V is the vacuum expectation value of phi naught. So this we are counting LR, right? So there is a LR coupling, that's why I have written it as off diagonal term. There is no LL coupling, right? No new LC bar, new LC. So this is 0. But this one, okay, couples new R to new R. So there is a term of order M. Okay? Roughly, this is the structure of the mass matrix. Right? This is actually 3 by 3. I mean, each of these you have to think of it as a 3 by 3 block. Right? But this is roughly the structure of the mass matrix. And if you look at the eigenvalues, just think of this as a one-dimensional matrix, or these are one by one block. Right? That will illustrate this problem. The eigenvalues roughly for large M, are lambda square V square by M and M approximately. And you see that here, if we take M to be large, then one of the eigenvalues is small. Right? Or for a 3 by 3 case, 3 of the eigenvalues will be small, 3 will be large. Right? 3 will be large because that they are of order M, 3 are small. Okay? And this was used to explain why the neutrinos have such low mass. Right? So the explanation was that not that the neutrinos have low mass, not because the lambdas are very small. Right? That is one way to make the masses low. But lambdas are order 1, right? Just the standard Yukawa coupling of the Higgs to the quarks and leptons. Okay? But if M is very large, okay, then that will make 3 of the eigenvalues very small. Okay, so this was provided as an explanation of why the neutrinos are light, right? Much lighter than all the other standard model particles.
The other eigenvalues,
those will be heavy, right? We don't observe them, right? If we take them, for example, for 10 to the 6 GeV, right? Or even larger, you certainly wouldn't be observing them today. Right? So this predicts that there are those other particles, right? But you don't observe them, right? And what you observe is very light. Okay, this is sometimes called the seesaw mechanism for neutrino mass.
Because this one term gets less mass and
other term becomes large, exactly, right? So one side goes down, the other side goes up. Okay, now you see that this term that you have added, okay, let's look at what it does under the lepton number transformation. Right? You have already introduced the transformation laws here, you cannot change it anymore. Right? These have been designed so that these terms are invariant under lepton number transformation. But now you see that mu r goes to e to the I theta times mu ri, right? That's what you have said there. Mu r c will go to e to the minus I theta times mu r ci, because mu r c already involves a complex conjugation. But then mu r c bar, that involves another complex conjugation, right? The mu r c bar is nu dagger gamma naught. So this will go to e to the I theta times mu r ci bar. So this term that you have written, well, there is Hermitian conjugation always, right? This term as you have written, this picks a phase e to the 2 I theta phase. So this violates L, and hence it also violates B minus L. So this then suggests that if this is the underlying mechanism for neutrino mass generation, right, then the same mechanism, the same Lagrangian, may be useful for producing B minus L in the early universe. And the precise mechanism that is suggested is that these heavy particles that we see here, right, as the universe cools down, at some point they will go out of equilibrium. Right, so you are already out of equilibrium. Then if you have also enough C and Cp violation, B minus L of course is not conserved, right? So then all the Sakharov's conditions are satisfied, and you may be able to produce B minus L in that process. Okay, how much B minus L you produce of course depends on the details of the parameters of the model, right? But given the parameters, you can work out how much B minus L will be produced in a given as the universe cools down. Is this point clear? So this is more or less the current understanding of how the baryon asymmetry was generated. Right? We know for sure that if the producing B is not enough, because standard model will wash it out, you have to produce something like B minus L, and this seems to be a natural mechanism for producing B minus L in the early universe. Well, baryon number, okay, this by itself says nothing about baryon number, right? This baryon number is conserved, right? So baryon number is conserved, lepton number is not conserved. So it produces lepton number, right? But then the standard model, because it can violate baryon number, right? It converts that lepton number into baryon number, right? Because B minus L is only conserved charge, right? So the same formula that I wrote down will be valid, right? With n B minus L given by minus NL. Whatever my lepton number you produce, you see what it contributes to B minus L. Right? That's the only relevant parameter. That's the n tilde L. And you use that to calculate how much NB that will be.
Why violating just B was not enough?
Oh, if you just violate B, okay, you have to violate B minus L. So if you only violate B, it's okay. But the SU5 grand unified theory, for example, you saw that it violates B, but it doesn't violate B minus L.
Okay, we want both.
We want B minus L. We don't care if B is violated or not, right? Because whether B is violated or not, that doesn't survive the equilibrium, right? Because what survives the equilibrium are only the densities of the conserved charges, right? Given the density of the conserved charges, the equilibrium statistical mechanics tells us the density of everything else. Okay. So this model also has experimental signature at low energy, because one of the things that people look for, right, to test this hypothesis, see, this implies lepton number violation, right? So one of the consequences of this model is that there should be neutrino-less double beta decay, right? In beta decay, typically you produce an electron, but also a neutrino, right, or anti-neutrino, so that the lepton number is conserved, right? But this model allows you to violate lepton number by units of 2. Right? So you can in principle produce 2 electrons or 2 positrons, right? That's the beta decay with no neutrinos, right? And you can, given the parameters of the model, you can actually calculate how much such at what rate you will see these neutrinoless double beta decays, right? You basically use that to put constraint on the this mass M, right? That you just, because if M is too low, then these neutrinoless double beta decays will be too prolific, right? Which you haven't seen. No, we have not seen, right? So you don't know for sure if this is the mechanism for neutrino mass, right? But this model is still a viable model, right? It has not been ruled out. And as I said, one advantage is that if this model is the correct model, it also could explain how B minus L was generated. Okay, so this is as much as I'll say about baryogenesis. So next time I'm going to start discussing dark matter, right? And now there are again various candidates for dark matter. I'll just describe one of them. Okay, that is what is called the weakly interacting massive particles. Okay, and the idea is that there are some massive particles Dark matter is consists of massive particles, and as the universe cooled, those massive particles at some point went out of equilibrium. And based on that, we will see how to calculate the density of such particles. Right? Once somebody gives you a Lagrangian, right, which has these massive particles in the spectrum, right, we'll learn how to calculate the current density of those massive particles based on the parameters of the Lagrangian. Right? What kind of calculation they need to do. The other alternative is this what is called the axionic dark matter, okay, where the particles are, instead of being massive, they are extremely light. Okay, and it's the coherent state of those particles that is supposed to be responsible for the dark matter. Right? That is not something that I'm going to discuss, but that's one of the project topics. If somebody is interested, can take up. The dark matter made of axions. Okay, so I think I'll stop here today. Are there questions? Okay, so then we'll continue tomorrow. Tomorrow? No. Yeah, next week. Yeah, okay.
So this B minus L variation will survive because at that time these massive particles will go out of equilibrium.
Yes, exactly. Right. The point is, when it is going out of equilibrium, right, B minus L violation should still be there. Right? If there is an equilibrium that is established after this process, right, which can violate B minus L, then again it will be wiped out. Right? So you have to make sure that when B minus L becomes a conserved quantity, right, that is the time when the system is going to out.